Alright, this is the video worksheet for 5.5 and 5.7. So let's take a look at number 1, which is up here. And number 1 asks you to compare the three figures, in this case the three triangles, and to figure out which ones are similar or they're to scale to each other, and then show me how you did that. So show me some work. What was your thought process? So can someone tell me which two are similar and how did you come to that conclusion? Well, there are two ways you can do this particular problem. The first way is what I showed you, is to compare two sides of any of the given triangles and then figure out if the ratios are in proportion. And that's the way I'm going to show you. But also, if you really looked at the two triangles, you would see that these two triangles have the same sides. This side and this side is the same. Same thing here. These two sides are the same as well. So right away, you know, these two are going to be in proportion without even doing any work. This one is the one that's going to stand out. But let's go the long way, in case you did it the long way, and we'll figure it out the long way. So let's take a look at the first one. Doesn't matter which two sides you compare, and at that point, you just have to stick to those sides. I'm going to choose this side and this side. So I have, you know what I'm going to choose? Yeah, that's fine. So 2 over 3 is the ratio of that side to that side. Sorry about the background music. You could have chosen any sides, but I just chose this and this. So I'm going to follow through and use the same sides for the others. For here, it corresponds to these sides right here, 3 and 3. For the last one, it corresponds to these two sides here, 4.5 and 4.5. Alright, and now it's pretty obvious which triangles are similar. This is 2 over 3. Both of these simplify down to 1. So these are the ones that are similar, because this simplifies down to just 1. And this one simplifies down to just 1. Make sense? Questions on number 1? So let's take a look at number 2. Number 2 is very similar to number 1. Here you are again asked to identify which two of the objects are alike, similar, proportional, or to scale. So once again, what's the first step to figuring this out? Well, you don't have a choice here because angles aren't really going to help you. They will have right angles. That doesn't really tell you a whole lot. So you have to use sides, and with rectangles there are only two relevant sides because two sides match each other. This one and this one is the same, this one is the same, so you have two sides to deal with, so it makes it easy. You don't have to worry which two sides you have to put into the ratio. The only thing you can do different is either put this one on top or this one on top. It really doesn't make a difference. So I'm going to go ahead and put the 4 on top and the 6 on the bottom. You could have went with 6 top, 4 bottom. Doesn't really matter. Alright, what can I simplify 4 over 6 down to? 2 over 3, because 4 is 2 times 2, 6 is 2 times 3, so I can cancel a 2 out of both top and bottom. Then the next one, again I don't have any choice in the sides I pick, but I'm going to have to put this one on top because I put that side on top to begin with for the previous problem, so I have to keep it consistent. And what can I simplify out of here? Again, a 2, 8 is 2 times 4, 10 is 2 times 5, so that's going to be 4 over 5. Alright, are those two ratios the same? No, they're not, so no proportionality there, which means these two are not similar, they're not to scale. Let's take a look at the last one here. Again, I'm going to put the 2 first and 3 goes on the bottom. Don't really have to simplify that one, that's the simplest form, but does it match one of the other ones? This one. So the first and the last triangles are similar, they are to scale, they're proportional, and the middle one isn't. Questions? Alright, number 3 is a little interesting. You're given 2 triangles. You're told that they are similar or they're to scale to each other. So they're similar triangles, which means they have proportions that are equivalent. But 2 of the sides are missing. That's interesting. We can't find it using the Pythagorean theorem, because for the Pythagorean theorem to work, you need at least 2 sides present, and you only have 1 side here. But because we know the other triangle, we can figure out at least one of the other sides that's missing. How can we do that? Well, we can set up ratios, and I want to make sure that one of my missing sides ends up in part of the ratio, because it wouldn't really do me a whole lot of good to compare the side I already know. So let's first look at, and I have to include one of the missing sides and one of the known sides. I can't include 2 missing sides. That wouldn't make any sense either. I can't compare a ratio that has 2 unknowns. So I'm going to call this missing side C, because it's the longest one, if you remember anything about right triangles. I'm going to call this missing side, B, just because, and that's going to be 2. So I'm going to set up my proportion. I'm going to compare first B and the known side to the corresponding sides on this triangle. So this is the ratio I'm going to set up. I'm going to say B over 2 equals to what? What are the corresponding ratio on this triangle? 5 over 4, of course. This corresponds to this, this corresponds to that. And now it's pretty simple. You guys know how to work this out. You simply cross multiply. We've done this many times before. So it's going to be 4b, 4 times b, equals to 2 times 5, which is 10. Then we divide both sides by 4, and we're not going to go too much into this, but if you were to do it, what would you get? 2.5. And again, you can do long division, but 2.5 fits into 10 4 times. Alright, so now we found B. Now we're looking for C. And there's 2 ways of finding C. It's a right triangle, and now you know 2 sides, you know A and B, or, well, you know the legs. You can use the Pythagorean theorem. That's kind of long. Why don't we do the same thing and find the other missing side? I think it's easier. Cross multiplying is a lot easier than chugging the Pythagorean theorem. So I'm going to do the same ratios, well, not the same, similar ratios, C over 2 this time. And what's the corresponding ratio on this triangle? 7 over 4. This corresponds with this, and this still corresponds with that, which means 4C, 4 times C, equals to 7 times 2, which is 14. It should be an arrow. And can someone tell me what is C equal to? What is 14 divided by 4? It's 3.5. And again, that one's a bit tougher, but it's an easy long division problem, so I'm not going to fret too much about it. So 3.5. So there we go. I found my first missing side. I found my second missing side, and all is well with the world. Questions? Alright, then let's take a look at number 4, which is right here. And I didn't write the entire problem here, but if I am not mistaken, you are having a picture that's being reduced, and it's going from 9 by 12 into 3 by something, and you're missing that something part. So you want to know what that missing measurement is. And you're told that this is a proportional reduction, so the two ratios have to be equivalent to each other. What do you do? Well, this one couldn't be any easier. You just set up the two ratios. They actually gave you the two ratios. 9 over 12 is the first one that they gave you. And then they gave you the second ratio. Oops, flying markers. The second ratio is 3 by something. The something, we're going to give it a variable. We're going to call it x, because x covers everything. Does a 3 go on top or bottom? 3 has to go on top because it's being compared to the 9. The 9 is on top here, and 9 goes first, the 3 goes first, the 3 has to be on top as well. You have to keep it consistent. The placement is important. And then of course x marks my missing second measurement. What do I do next? I'm going to cross multiply, and I'm not going to spend a whole lot of time on the little details here because I'm hoping that you guys are familiar with cross multiplication by now. So it's going to give me 9 times x, which is 9x, equals to 3 times 12. And can someone tell me what's 3 times 12? Oh, you know what? I'm going to write it out here. And let's do it in 2 steps. So what is 3 times 12? 36. And then of course I'm going to divide both sides by 9. So what is x equals? 4. That's my missing measurement there. So x is 4. So the new picture, once it's reduced, it's going to be 3 by 4 from 9 to 12. Equivalent ratios. Questions on number 4? Then let's take a look at number 5, which is right here. And number 5 tells us there's a scale. 1 centimeter is 5 kilometers, and I think we're reading a map in this problem. So they tell you that if you move 6 centimeters on the map, how far is that in real life? Not a problem. The scale acts as one of your ratios. Since it's to scale, it's automatically proportional. So it's kind of neat like that. So you set up your first ratio, 1 over 5, and then you set up your second ratio, except where does the 6 go, top or bottom? Top. And top because the 1 represents the centimeters. So the centimeters, if their centimeters are on top here, they have to be on top here. I could have flipped this. I could have said 5 over 1, and then the centimeters would be on the bottom. Then I would have put the 6 on the bottom too. They just have to match. They just have to match. The relative position is not that important. You just have to make sure they're all matched up. And our missing real distance in kilometers, again, I'll just give it, well, I'll give it k for kilometers, I guess. Let's not overuse x. What do I do next? Cross multiply, and this one is a real simple cross multiplication because k times 1 is just k. 5 times 6, well, that's just 30. Hey, look, we found it. How easy was that? One of the easiest problems I've ever given you. You're welcome. So our missing measurement is 30 kilometers. If you move 6 centimeters on the map, You actually move 30 kilometers in the real world. Questions on 5? Last sets of problems, and you have another representation of my artistic skill at work. So here we have a building, and we're told that it's a model of a building. And they do this often. Whenever they build something new, they first create a model, and then they base the real building off the model. And the model has the following measurements. The base, or the length, is 6. The width is 3, and the height of the building is 5. So if the real building has a length of 1200, so the real building is going to be 1200, whatever units long, the units that are important in this case. What are the other sides? What are the other measurements? What would you do first? This is actually very similar to that one problem that we did with the triangle that had the missing sides, that one, number 3, because once again you have one object that has all 3 sides present, then you have another object that has only one side given to you. They're not triangles, but that shouldn't really stop you. So I'm going to set up my 2 ratios. The first, and it doesn't really matter which ones you compare. I'm going to compare one of the sides that I know. So I know the length of the new building. So I'm going to compare the length of the model and the width. Again, it doesn't really matter which way you start. So I'm going to say 623. The ratio of this to this equals to 1200. Now that's the length. Corresponds to this, and this is on top now. And now I'm looking for the width of the real building. So that's going to correspond to the 3. I don't know what it is, of course. I'm just going to use a W for the width. Why not? And I'm just going to cross multiply. That shouldn't be too difficult, I hope. That gets us 6W equals to 3 times 1200. What's 3 times 1200? It's like 3 times 12 with 2 zeros. It's 3600. And then I'm going to divide both sides by 6. What's 3600 divided by 6? It's like 36 divided by 6, but with 2 zeros added in. So it's going to be 600. So W, the width of the new building, or the final building, is going to be 600. Whatever units they're using. Feet, inches. Probably feet, because I'm sorry, probably inches, because that'd be a lot in feet. Unless it's a really big building. I don't know. Alright, that's the width of the new building. Well, we still have the height. Because they gave us the length, we just found the width, now we want the height. How can we find the height? In the exact same way we found the width. We're going to set up our 2 ratios. First, I'm going to set up a ratio of, now it doesn't really matter, I can use the 6 or the 3 because I know both the width and the length. Let's go with 3/5. So I'm going to use the ratio of this to this, so the width to the height of the building. And this probably might be a little different depending on which way you went in your problem. And I know my width. I just found out what the width is. What is the width of the new real building? It's 600. It is 600. What is missing now is the height. I don't know what the height is. I'm going to use an H for the height. And instead of using the 3 and the 600, I could have still used the 6 and the 1200, so I could have went 6/5. You know, lots of ways to do this. Once you know another piece of information, you can use that in your problems, or you can stick to what you knew originally. Up to you here. I'm going to cross multiply again. which is going to yield 3h equals to, what's 5 times 600? 3,000. And when I divide both sides by 3, what's 3,000 divided by 3? It's like 3 divided by 3, but with 3 zeros. 1,000. So now I have all my missing sides of the new building. The new building will have a length of 1,200 that was given, a width of 1,600, and a height of 1,000. Questions on how we did number 6? That was a little bit tougher, I guess. If not, let's tackle number 7. 7's next. Alrighty. With number 7, you are given another picture, and you're told it's being enlarged from 3 by 5 into 11 by something. That happens quite a bit. You have a small picture, you take it to a Photoshop, not the program, but an actual place that deals with photos, and they enlarge it for you. They blow it up, they make it larger, so you can see more detail or whatnot. This is one of my mistake problems, which means I actually worked the problem out for you, but I made mistakes. In this case, I think I made 2. Can someone point out what were those 2 mistakes? Well, the first mistake is the way I set up my ratios. Here I have 3 by 5. 3 is first, 5 is second, 3 went on top, 5 went on the bottom, and then it's 11 by I don't know what. The 11 is first, the 3 was first, the 3 went on top, the 11 should have went on top as well. I did not put my ratios in the right places. So that's my first mistake, and that will make a difference. That will definitely make a difference, because when I cross multiply, then it would be 3 times x and 5 times 11. That'll make mistakes of their own. But if you follow through, I made another mistake somewhere here in my divisions. So even if this problem kept going, there was another mistake made right here. I divided incorrectly. 5 goes into 33 6 times to give me 30, not 5 times. 5 times 5 is 25, not 30. So that right there should have been a 6. And then I make that mistake again here. What goes into 30? I mean, how many times do I have to multiply 5 to get to 30? 6 again. So that should have been 6.6. Still, that would be wrong because I made that original mistake here, but regardless, I made 2 mistakes, and there they are. Questions number 7? You'll probably have one of these types of problems where I make more than one mistake. So even if you find the original, you may want to shuffle down and see if I made another mistake, regardless of the first original mistake. Alright, last problem here. We're pretty much done. Real life uses for scale and similarity. So what did you guys list? Give me some ideas. There are so many ways you can use real life scale and similarity. We already mentioned photo resizing. And this is an important one, and this happens automatically in most programs we use on the web today, but they use a mathematical algorithm that uses ratios and proportions when they resize. So when you upload a really big image and they automatically downsize it because they don't want, host a 5 megabyte version of your picture. They want to, scale it down to like, 200 kilobytes so it doesn't take up so much space on their server. They'll do this automatically. Facebook, Instagram, whatever the case may be. You take a picture with your phone. It's usually much bigger because, you have this giant 8 megapixel camera that throws in a bunch of information. The website doesn't want all of that. It automatically resizes it. So that's a good thing. Otherwise, the web would be full of these big giant images and it would be all slow and crashy. The second is in building of really anything. So you can say building, could be houses, could be building spaceships, could be building satellites, almost anything today that's built. There's a model of it built first, and the model gives you kind of a safe way to build something that takes significantly less resources. It's easier to manage. And if you're building a brand new park, you'll create a model of that park. You can probably fit it inside a room, you know, and people can look at it, they can make additions to it and corrections, and then you can, you know, build a real version of that. Maps is another one I can think of. Every single map is essentially a similarity of a landscape that it covers. You look at the map of the United States, for example, and it is essentially a proportional similarity to the real landscape of the United States. But you can navigate a map, you know, the map can unfold and be the size of your, let's say, kitchen table, while, you know, the landscape of the United States is a little bit bigger than your kitchen table. But it's useful because then you can kind of see what the relative distances are between two cities, two states, how long it'll take you to drive there based on all the proportions. So maps are also another use, and there are many more, and you might have given me some others. So any questions on number 8? All right, thank you very much. Have a great day.